So today we're going to be looking at something called Lewis structures. And we started this look at the layout of the periodic table by considering the number of valence electrons that an atom has. And let's remember that valence electrons are the ones in the outermost energy level. And so yesterday we were developing our shorthand for indicating how many valence electrons an atom has was something called an electron dot structure, or an electron dot notation. And we've got a new way of looking at the periodic table. There is a new numbering system, and all we have to do is look at this new numbering system to determine how many valence electrons an atom has. So we know that carbon has got 4 valence electrons. We know that something like nitrogen, which is in what we are now calling group 5, has 5 valence electrons. We know that oxygen, which is in what we are now calling group 6, has 6 electrons, and so on and so forth. So what are we going to do with this thing called a Lewis structure? Well, it has to do with how electrons are distributed in bonding. Let's remember that atoms form bonds for one purpose. Atoms form bonds which involves the sharing or swapping of electrons to fill the outermost energy level, what we're going to call the valence. And let's remember that the magic number here is 8. This is why elements that are noble gases like neon don't typically form bonds with anything. They are inert because they already have 8 electrons. So we're going to try to do this in such a way that everybody's got access to 8. And we're going to call this the octet rule. It's a real simple rule. It looks like this. Atoms will lose or gain electrons, and that can involve sharing as well, in order to ensure that the valence, which is the outermost, has access to 8. I'm going to put an asterisk here because we should be paying attention to this fact that there are always exceptions to this rule of 8, but we'll get to that. A good example of an exception would be an element like hydrogen, which can only hold 2 electrons. So whenever we see hydrogen, we're not going to worry so much about filling it with 8 because it can't hold 8. So what's a Lewis structure, and how does this work for showing us this distribution? It's real simple. So what a Lewis structure does is it helps us to visualize how we distribute electrons to make sure that everybody's got access to 8. Remember, there's an exception to that. Let's take a real simple molecule, and I'll show you how this works. We're going to break this down into a couple of steps. So here's a molecule called carbon tetrafluoride. It has, as you can see here, 1 carbon and 4 fluorines. And so what we want to do is we want to ask how the electrons are distributed in this molecule to give everybody access to the 8 electrons. That is the octet rule. So the first step that we're going to do is we're going to count all the electrons that are in the valence. That is all the outermost energy level electrons. And we know by looking at the periodic table that carbon has 4 electrons in the valence, and that each fluorine has 7, and there are 4 of them. So this means that for the valence electrons, we have a total of 28 from the fluorine, 4 from the carbon. That's 32 electrons to play with. The next thing that we're going to do is we're going to draw a skeleton structure. Kind of appropriate given the season. Whoops. And what the skeleton structure does is it shows us the basic layout of all of the atoms involved. Typically, if we have one of any particular element, that's the one that goes in the middle. So I'll put the carbon in the middle. And then the skeleton part is going to be showing where the atoms that are bonded to the carbon are distributed. We're going to use a single line to represent a bond involving 2 electrons. So that means that each time we see a line like this, that's 2 electrons total. So Obviously, the bonding occurs when we share electrons, and each of these fluorine atoms is sharing 2 electrons with the carbon. So that means that of our 32 electrons, we have used a total of 2, 4, 6, 8 electrons in the bonding. And that means that we have 24 electrons left to play with. So what we want to do is use those 24 electrons that we have left to fulfill the octet rule for every atom involved. So here's what we're going to do. Of these 4 fluorine atoms, they each have 2 electrons involved in the bonding, and there are 24 electrons left. So what I'm going to do is use an electron dot structure to show how the remaining 24 electrons are filling the octet. So of the 24, we use 6 around this fluorine. That means we have 18 left. Of the 18 left, we're going to put 6 around this fluorine. That means we have 12 left. Of the 12 left, we'll put 6 around this fluorine. And now we have 6 left, and they'll go here. And all I'm doing is trying to fulfill this octet, so I'm going to double check. We know that the carbons all have access to 8. Well, there's only 1, and it has access to all the electrons involved in the bonding. And sharing, stealing, it doesn't matter, as long as it's got access to 8. We also know that each of these fluorines has access to 8 because it has the 2 involved in the bonding, and then, of course, the remaining 24 that we just distributed around each to fulfill the octet. So our final step will be to draw the Lewis structure for this, and we're only going to worry about the electrons that are bonded to the central atom. We're not going to be paying attention to anything bonded to the outermost ones. So our final step, after this distribution of electrons, we should say that step 3 is to distribute the electrons to fill the valences. And that finally our step 4 will be to draw the final structure, which is our Lewis. And that's going to involve simply the central atom and any electrons that are around the central atom. In this case, all the central atoms' electrons are bonded to fluorines. Pretty straightforward, right? Let's try another one. This one's going to be a bit more familiar. Okay, here's a molecule that we're all familiar with. This is water. It has 2 hydrogens and 1 oxygen. So let's remember that our first step is to count the electrons in the valence. We have 2 hydrogens and they each have 1 valence electron. We have 1 oxygen and it each has 6 electrons in the valence, so we have a total of 8 electrons in the valence to play with. Our next step is going to be to draw our skeleton structure, which is simply going to involve a basic layout. We'll take the atom we have the fewest of and put it in the middle. That's our oxygen. And we'll put a hydrogen on each side. And the skeleton involves how many electrons are involved in the bonding. Well, we put a pair of electrons here and a pair of electrons here. That means that we have used up 4 electrons in the bonding, and we have 4 left. All right. Our third step is to distribute our remaining electrons to fulfill the octet of every atom involved. Well, the hydrogens can't have an octet. All they can hold is 2. And since we already used 2 electrons in the bonding, that means these hydrogens are all set, so we don't need to worry about them. What we are going to do is take these remaining 4 electrons and we're going to put them in such a way that it fulfills the octet of the final atom remaining, which is the oxygen. And we'll put them around the central atom. And so our final Lewis structure is going to look like this. And we're going to pay attention to the fact that these electrons remaining around the oxygen, what we're going to call lone pairs, because they'll be important later. So what's the Lewis structure for this particular molecule? It simply looks like this. we'll keep in mind these lone pairs around the central atom. Okay? Let's do one more because there's one more trick we're going to use. All right, let's do this last one. And this one looks a little strange. If you're wondering where I got this from, this comes right from your list of polyatomic ions on the back of your periodic table. And it is called the carbonate ion, and it has a charge of -2, meaning it has 2 extra electrons. So what we're going to do is we're going to draw the Lewis structure for something like this, and you'll see there's a little trick that we can use. So the first thing that we're going to do is we're going to count our valence electrons. We have 1 carbon that has got 4 valence electrons. We have 3 oxygens. Those each have 6, so for a total of 18. And we have these 2 extra. So, how many electrons total? We've got 4 plus 18 plus 2. We've got a total of 24 electrons to play with, right? 18 plus 4 is 22, plus an extra 2 is 24. So, our second step is going to be to draw our skeleton. I'll leave that up here. So, our skeleton, we'll take the atom that we have the fewest of, and we'll put that in the middle. And we'll skeleton our oxygens with a pair of electrons each. So we've used up 6 electrons in the bonding, and that means that now we have 18 electrons left. So of the 18 electrons that we have left, we're going to distribute those around the atoms involved so that we can fulfill the octet. It doesn't matter where we start, so I'll start with the oxygens. So, of the 18, I'll put 6 around this oxygen. We have 12 left. Of the 12 left, I'll put 6 around this oxygen. That means we have 6 left, and of the 6 left, I'll put around this oxygen, and we are out. We have no more. We've used up all 18. So let's check. Does this oxygen have access to 8? Yep. So does this one, and so does this one. The problem is that the carbon only has access to 6. No bueno. So a neat trick is what we're going to call a double bond, because each of these oxygens, this guy, this guy, this guy, they all have these extra electrons floating around the outside. We don't really pay much attention to them because they're around outer atoms, but that doesn't mean that we can't use them. So what I'm going to do is I'm going to take this pair of electrons around this oxygen. I could take any one, it doesn't matter. And I'm going to drop them here and share them with this carbon. Because now this oxygen has 8 and this carbon has 8. This is what we call a double bond, and there's no rule that says we can't do that. So the last thing I'm going to do is I'm going to draw my skeleton involving this new trick called a double bond, and we're not going to worry about any electrons around the outer atoms. We're just going to worry about the central ones. And so the Lewis structure for this looks like this. You could put that double bond anywhere you wanted, and it wouldn't matter. And each of these would be equivalently valid. Doesn't matter where. In fact, your textbook refers to these as something called resonance structures, because what it's saying is each of these Lewis structures is equally valid, and it doesn't matter where we put the double bond. Okay, it's a good trick. I'm going to ask you guys to practice this. So best of luck, and I'll see you on the next one.